In a study published on June 14th, researchers looked at the composition of dust grains collected from Saturn's E-ring that came from the ocean of Saturn's moon Enceladus. In this video, I'm going to break that paper down. I'm Cameron and this is my channel. Welcome to the Sexy Universe. First, real quick, a few things about Saturn. It's a gas giant and it's visible with the naked eye, and that makes it one of the most studied objects in our solar system. It's also incredibly beautiful, with this very elegant system of rings and moons surrounding it. The dust particles analyzed in this study were collected by the Cassini spacecraft, which was launched in 1997. This page is from NASA's website. The image on this page is rotatable, so you can see it from every angle. And you can also use it to see the location of the cosmic dust analyzer. The cosmic dust analyzer is shaped like a bucket, a very small bucket, and contains a mass spectrometer. I'll explain how a mass spectrometer works later in this video. This image from NASA's website shows Saturn and its ring structure. The rings are labeled A through G. The first rings to be discovered were the A, B, and C rings because they're the most visible. They can be seen with just a regular telescope. And in fact, you can see that there's something there just with your naked eye. The innermost ring is the D ring, and then outside of that core group of A, B, and C are the F and G rings. The E ring is the most diffuse, it's the most spread out. And you can see outside of the G ring, but before the E ring is Mimas. And then you can see Enceladus and Saturn's other moons going out further. The E-ring is the largest and most diffuse, but that also means it's very difficult to see. And even with most telescopes, it's probably only going to look like a haze at best. The Cassini spacecraft passed by Enceladus several times, and it was able to take hundreds of photographs of plumes coming from the southern pole of Enceladus. And we know from analyzing the absorption spectra of those plumes and dust grains in the E-ring that they are composed of the same elements. Researchers concluded that the E-ring of Saturn is formed by ice grains escaping Enceladus's plume into orbits around Saturn. And hence the analysis of these grains by the cosmic dust analyzer proves important insights into the composition of the subsurface ocean, including a rich variety of organic compounds. And basically what that quote is saying is that the E-ring is being produced by Enceladus, and the ocean under the ice of Enceladus is going to have the same composition as the particles in Saturn's E-ring. As I mentioned earlier, the entrance of the cosmic dust analyzer is shaped like a bucket, and within that cosmic dust analyzer it has a mass spectrometer. At the front end of a mass spectrometer, where particles enter, there's a laser that detects them as they come in. In this image, the red particle is heavier. It has a longer arrow on it because even if the particles are coming in at the same speed, the red one is going to have more momentum because it has more mass. At the back of the spectrometer is a deflector. That deflector is basically a charged electric field. So when charged particles come up to it, they're going to be deflected by that field. The red particle travels further into the field because it has more momentum. And after the particles are deflected, they fly into a detector. Because the heavier particle went further into the electric field before being deflected, it's going to have a longer time of flight. It's going to spend more time flying through the spectrometer. The detector on the cosmic dust analyzer was a rhodium diaphragm, and rhodium was chosen because it's non-reactive. Of all the particles that Cassini was able to analyze, the researchers found 345 of them interesting enough to look at for this study. Of those, 9 were found to be unusual in their composition. This graph shows the mass spectrometry results for those particles. The horizontal axis shows the time of flight in microseconds for these particles, and the peaks in the graph correspond to specific compounds. You'll notice the chemical formulas of these compounds with numbers assigned underneath them. Those numbers are the atomic masses of these compounds. So for example, this first compound is sodium ions with the number 23 assigned to it. 23 is the atomic mass of sodium. And you'll notice that there are these other compounds along the way, and 3 of them on the far end are phosphate compounds. So we have a mix of data from 2 different experiments that are giving us these results. From photospectrometry, we know what elements are there. And from the mass spectrometry, we can know what the proportions are. And once we know what the elements and the proportions are, we can figure out what kind of compounds they're forming. And in this case, it was a lot of sodium phosphates. The ideas in these two graphics are a little bit more complex, but I'll do my best to explain them. I mentioned that they only found 345 dust particles that had been collected by Cassini to be pertinent to this study, and 9 of them were phosphorus containing. The other 336 contained carbonate compounds. And when you talk about the acidity of a body of water, the concentration of carbonates is very important. And in fact, the more acidic water is, the fewer phosphate compounds can dissolve in it. They assumed the composition of these particles were representative of the ocean water under the ice of Enceladus. The area in pink shows the possible range of concentration of total phosphates. The area in blue shows the possible concentrations of total dissolved carbonates. And this area where the two cross is the possible composition of the ocean on Enceladus. You'll also notice that they have a few possible equilibrium lines drawn within that. And those are based on assuming that the rock geology on Enceladus is similar to that of Earth. They also assume that the temperatures were above freezing, so above 0 degrees Celsius, or 32 degrees Fahrenheit. The image on the right shows the lines of possible carbonate concentrations in that ocean based on the phosphate concentrations that were discovered in the particles. Another way to show this is with a Venn diagram. If we look at all the possible states of dissolved phosphates and all the possible states of dissolved carbonates, then where the two overlapped are the possible states of the ocean. There's still a little bit more to discuss about this paper. If you're enjoying the content so far, please click the like button and leave any thoughts, questions, or comments you have in the comments section below. It helps the YouTube algorithm, and I want to hear what you think. Now I'm going to read a few money quotes from the discussion section of the paper. The first quote is, "Even with a conservative margin, our estimate indicates concentrations in the order of at least several hundred-fold the average phosphate abundance in Earth. Of the 6 elements, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, that are considered to be critical ingredients for life based on water and organic chemistry, phosphorus is cosmochemically the least abundant and has not previously been detected in any ocean-bearing moon in the solar system. However, the results presented here demonstrate that Enceladus has a high availability of dissolved phosphorus, which is extremely unlikely then to be a limiting factor in the survival of life on Enceladus, and perhaps also other ocean worlds that reside beyond the carbon dioxide snow line in the solar system." When they talk about the abundance of phosphate on Enceladus in the ocean, what they're referring to is this. This is a DNA molecule, or at least a structural drawing of one. And you'll notice along the backbone here, there are phosphorus atoms. And basically phosphorus, along with these sugar molecules, make up the backbone of DNA, which, as you know, is kind of the software of life. Another phosphorus-containing molecules that living beings rely on heavily is ATP, adenosine triphosphate, which, as you can see, contains 3 phosphate groups. ATP is the energy-carrying molecule within cells. So without ATP, without the presence of phosphorus, our cells cannot carry out the functions necessary for life. Another concept the authors talk about is the CO2 snow line. The CO2 snow line is the boundary around our sun beyond which the temperature is too cold for carbon dioxide to be in a gassy state. Instead, that carbon dioxide turns to ice and would fall to the ground as snow. What the authors argue is that objects beyond that snow line would have a better balance of carbonates dissolved within them. They would have better acidity buffers, and therefore they could have more dissolved phosphates, while objects within that snow line would have much, much lower levels of phosphates. So they argue that searching for the building blocks or signs of biological life in our solar system that search should focus on objects that are beyond the CO2 snow line. I hope you enjoyed my discussion of this research. I'll make the show notes available on my website, thesexyuniverse.com. I'll put a link to the page in the description, along with a link to the original research paper. If you had a good time today, please click the like and subscribe buttons. Leave your thoughts in the comments section if you haven't already. If you want to support my work, the best way you can do it is by watching my videos on YouTube. You can also follow me on Instagram and TikTok. My handle is @camwadam, CAMWADAM. And if you're feeling particularly generous, you can send me a couple dollars on Cash App. As you probably know, our knowledge is always increasing and new research is always coming out. I do my best to stay up to date and post new material whenever I can. So keep getting smarter and stay on your game, and I'll see you next time on The Sexy Universe.